Hello, my name is Benjamin Mattson. In this presentation, I'll be walking you through a database-driven system that I've developed to improve how we track production data at Teledyne Marine. This project was part of my work for the DSC 550 course, and it also addresses a very real need in our company's manufacturing environment. Specifically, I focused on improving how we capture, store, and visualize test and assembly records for our most complex underwater vehicles. Teledyne Marine designs and manufactures advanced undersea technology for applications ranging from ocean research and environmental monitoring to meteorological data collection and defense. One of our core products is the Slocum Glider, which is an autonomous underwater vehicle that can operate at depths of up to 1,000 meters and can be configured with a wide range of sensors. Each unit is built to order, meaning every vehicle is different and requires extensive testing and traceability throughout the production process. That complexity makes good record keeping essential not only for internal quality control, but also to ensure mission success once these systems are deployed in the field. For many years, we've tracked our assembly and test data using physical binders, known internally as blue books. Each binder held all the paperwork for a single vehicle, but as production has scaled up, this method has become unsustainable. Some teams have transitioned to using Excel spreadsheets, which helped, in theory, but the files were protected and poorly standardized. We saw frequent issues with overwritten data, inconsistent formats, and files getting lost or duplicated across teams. This led to gaps in our records, and at times, it even put customer missions at risk because we couldn't quickly trace which components had passed which testing. To address this issue, I've developed a system that combines a secure SQL Server database with a customized Excel interface powered by VBA. The database stores all serial numbers, assembly relationships, and test records in a structured format, while Excel acts as the user interface for technicians to enter data from the production floor. The system was designed to be scalable, traceable, and easy to use, providing management with better oversight and ensuring that every part of a build can be traced and verified long after the product has left our facility. Starting on the Excel main menu, I'd like to now demonstrate how a serial number will be requested. In this case, we're going to test it with a deep forward section. First, we double-click on the cell, and the form pops up. This form will be filled out with some test data, a part number, a quantity, in this case, let's just say 3, a customer order. This is both a drop-down and an entry field, so in this case we will do 987, and technician initials. When I submit this form, the VBA code packages the input data and sends it back to the SQL database using a secure SQL connection. The serial numbers are then automatically generated in the serial number table and echoed back to the technician. If we transition over here to the SQL database, we can open the serial log for the forward section, and we can see the three entries that we had just created, 19, 20, and 21. Returning now to the Excel main menu, we're going to demonstrate how an assembly record is entered. In this case, we're going to do an AFCAP. So again, we double-click in the cell, and we are presented with the serial number for the AFCAP that we'd like to enter assembly information for. In this case, we will just select serial number 10,004. We are going to choose yes to enter assembly information. This assembly form is customized specifically for the AFCAP, which includes both serialized assemblies and off-the-shelf components. The drop-downs that we see for the radome fin and thruster are dynamically populated from the SQL database, ensuring that only valid serial numbers can be used for each field, while these free text fields are supposed to be used for lot or batch tracking of anything that is purchased and comes in with a serial number already applied. For the purpose of this, we're going to use some sample data. This is just an example, and we're going to select 10,004 for the serial numbers for these parts as well. This doesn't always need to be the same. This is just an example. When I submit this form, all the values are written into the assembly log aft cap table, creating a complete historical record of that assembly. Here in the SQL database, we can look into the assembly log for the aft cap table, and here we see aft cap serial number 10,004 with the air bladder lot, pressure transducer serial number, radome serial number, thruster serial number, timestamp, and technician initials. Again, starting from the Excel main menu, we will now display how a test record entry works. In this case, we'll be testing a ballast drive. We'll be entering a serial number that already has test information, so it is going to automatically clear it, give us a blank form for us to enter. We are now going to enter this test record, and this form has built-in logic to help reduce any human error. For instance, if a voltage is too low, it will automatically trigger the failure status, and the pass-fail cell is then color-coded in real time to give immediate feedback to the technician. In this case, we are going to just enter some arbitrary data. And when I submit this data, all of the test fields here are structured into a JSON object and saved to the test log table in the SQL database. This design allows us to store variable test formats in a single column, while still being able to search and query based on individual fields within that JSON field. We're going to re-execute this to see that information again. And here, we see the test ID is log number 53 for serial number 10,002, and it shows us all the data that we had just entered. One unique feature of the Glider serial number form is that it doesn't just create serial numbers in the database. It also creates a structured file system behind the scenes. When a technician requests Glider serial numbers, the form automatically generates a customer-specific folder on our internal file server, named according to the customer and vehicle ID. This ensures that all associated records, test forms, documentation, and final reports are consistently stored in one place from the moment that this vehicle is created. We see here this is the folder that was created for the next serial number taken from the Glider serial number log. This reduces the risk of misplaced files and makes it much easier to retrieve documentation later, whether for engineering, service, or auditing purposes. The Glider test form goes a step further than all the other test forms. Instead of just entering values into a generic test form, this process generates a dedicated serial number specific Excel file for each Glider. When a technician selects a Glider serial number from the list, the form not only loads relevant data from the database, it also opens a pre-formatted Excel workbook linked to that unit. This form ensures the correct file structure and test steps are used every time. We see that after the file has opened and saved, it is saved from our rev controlled location and saved to our customer specific folder. The technician can then enter all the data they need to and save it. Once the technician completes testing and submits the form, that file is saved directly into the corresponding customer folder with a file name that ties it to the exact vehicle and procedure. Going back to that same file location, looking in the correct section, we see that this file was saved right here with the form number and the serial number of the vehicle. This approach provides a clear, traceable workflow and keeps our digital records clean, consistent, and very easy to reference. What sets this project apart is how it balances flexibility and control. The forms dynamically adapt based on the part type. The database ensures relational integrity without bloating the schema, and test data is stored in a way that supports many formats without requiring dozens of individual test tables. This design allows us to support a wide range of products while maintaining consistency and minimizing maintenance overhead. Now that we've seen how data is captured and stored, I'd like to show how that information is made useful through dashboards. These dashboards are built directly into Excel and are automatically linked to the SQL database. They help both managers and technicians quickly assess production status, tracking test progress, and identify any units that may need follow-up. On the left side here is the glider dashboard. At the top, we have KPI cards summarizing production over the past 30 days. These include counts for the total gliders built, the average completion of those glider builds, and the number of incomplete builds. Just below the KPIs, we have a bar chart. The bar chart shows a serial by serial breakdown of test progress. Each bar is color-coded, green for completed tests and red for missing data. This makes it immediately obvious which gliders are falling behind and which are ready to ship. At the bottom, we have a pie chart which gives a simple snapshot of testing coverage, how many gliders have been built and tested, and how many have been built but not yet tested. This format allows supervisors to quickly gauge overall readiness without needing to open any records. Over here on the right side, we have the forward section dashboard. This second dashboard focuses on the forward sections, which are built in both deep and shallow variants. The format is exactly the same as the glider dashboard, meaning that this consistency makes it easy for users to navigate between product lines without learning a new system. We again start with KPIs for the last 30 days, followed by bar charts showing test coverage for each serial number, and finally, pie charts that show built versus tested ratios. The side-by-side format makes it easy to compare deep and shallow builds at a glance. Whether you're a technician tracking your daily workload or a manager planning deliveries, this layout puts the right information in front of the right people. These dashboards are more than just visual aids. They're decision-making tools. By tying real-time test and build data directly into these visuals, we've created a system that improves visibility, speeds up troubleshooting, and ensures accountability across the production process. To wrap this up, this system was designed not just to digitize a paper process, but to fundamentally improve how we capture, validate, and access production data. By integrating an SQL database with a familiar Excel interface, we've created a tool that technicians can use with confidence, and that managers can rely on for insight. Every form submitted is traceable. Every test result is structured. Every build is backed by reliable data. The dashboards make this data immediately useful. They eliminate guesswork, support better planning, and highlight issues before they become problems. What makes this system unique is its balance. It's technical under the hood, but accessible on the surface. And because it was built with scalability in mind, it's ready to support new part types, new processes, and new teams as our needs grow. Thank you for watching and for the opportunity to share a system that I'm proud to have built.